Okay, we're at a big turning point in these live lessons. So everything that we've been covering up until now has been focused on probability theory and a little bit on information theory. For the remainder of these live lessons, we're focused on statistics that are relevant to machine learning specifically. And so we're going to apply the probability theory that we learned to quantify the differences between distributions, to quantify the relatedness of distributions, and to confidently reject or approve hypotheses. For example, to select a particular machine learning model despite uncertainty, despite noise. So here are the key terms that we had in the probability content that preceded now. And so take one last look, maybe take a screenshot if you really want it, because we're going to now erase most of these terms to make room for some new statistics terms. I'm only going to leave on the board the most important key terms, the absolutely essential ones for moving forward with the statistics content. So I'll be referring back to those terms a lot, but all of these terms will be useful in your machine learning journey. We talked about the field of statistics at the beginning of these live lessons, but that was so long ago that it's time for a quick refresher on the key concepts. So let's talk about Bayesian statistics first. Remember that Bayesian statistics can incorporate prior knowledge that we might have. And the kind of terminology, the kind of way that we can describe thinking about Bayesian statistics is the way that untrained people, that lay people talk about probabilities, saying things like, there's an 80% chance it'll rain today. And Thomas Bayes is the namesake of Bayesian statistics. In 1763, he came up with Bayes' theorem, which we'll talk about right near the end of these live lessons. But it was Pierre-Simon Laplace, pictured here, who in the late 18th and early 19th centuries defined a lot of the groundwork for Bayesian statistics. And so lots of applications beyond just this standalone Bayes' theorem. Recall that some drawbacks of Bayesian statistics are that some people think beliefs are icky. So having prior knowledge incorporated into our models, some people don't like that idea. And generally, Bayesian statistics is computationally expensive. Computationally expensive relative to what, you might ask? Well, relative to frequentist statistics. So frequentist statistics focuses on quote-unquote objective probabilities. And frequentist statisticians have funny ways of thinking about probabilities. So if they were to say, make a prediction about whether it's going to rain today, instead of saying something more straightforward like a Bayesian statistician, they might say something like, on 100 days exactly like today, it would rain on 80 of them. So the thing about frequentist statistics that is both very predominant but also a little bit controversial today with our larger data sets is the significance threshold. So the significance threshold has kind of a standard threshold. We're going to talk about that in a lot of detail shortly, but it is kind of arbitrary. And with the big data sets that we have today, it's very easy to have supposedly significant results, which is also part of why I don't know how objective frequentist statistics really is. So the big names in frequentist statistics, Siméon Denis Poisson in 1837, whom you may also recall now from the Poisson distribution. In the 19th century, frequentist statistics was expanded by big names like Mill, Venn, and Boole. And in the 20th century, the two big players are R.A. Fisher and Carl Pearson. So generally speaking, an advantage of using frequentist statistics is that it is computationally inexpensive. A lot of the work done on it in centuries past was done by hand, and we ourselves are going to go through a lot of exercises by hand to get you familiar with how these concepts work. So statistics and machine learning are two separate fields in a way. They both build on the probability theory that we've covered in order to make inferences under uncertain conditions. So why do we need statistics if we have machine learning? Well, I'll tell you why. They work very nicely hand in hand together. So statistics is very useful for examining data distributions, including the outputs of our models, whether they're statistical models or machine learning models, as well as considering the distributions of our prospective inputs into our models. This practice of examining our data distributions enables us to deepen our understanding of the data that we're working with. It allows us to identify irregularities in the data, maybe problems in the way that we were collecting our data, and it allows us to reshape our inputs toward standard normal. And we talked about that earlier in these live lessons in the context of all of these distributions. Near the end of talking about that, I talked about how we can reshape our distributions towards standard normal and how that's often helpful in machine learning situations. It allows our machine learning models to learn more quickly, maybe even converge upon better model parameters. On top of allowing us to examine data distributions on their own, it also enables us to examine relationships between data, so between different inputs or maybe inputs and outputs. And so this can guide our overall modeling approach. And we can also use statistics to compare our model performances. So we might have two different machine learning models that are performing slightly differently, but because the machine learning models are stochastic, we get not exactly the same results every time. And so we could develop two different distributions of results. And then if we want to compare, is one distribution of results better than the other? Is one more accurate than the other? Or does one perform more quickly than the other? Then we can use statistics to tell the difference with confidence. We can also use statistics to ensure that our model isn't biased against particular demographic groups. So we can compare, how do my model outputs vary when I have men as the inputs or women as the inputs, or a particular racial group versus another racial group. And in a lot of cases, you want to make sure that your model does not perform differently for these different demographic groups. And statistics gives us a tool for saying, okay, are these differences between these groups statistically meaningful or not? Finally, as we mentioned early on in these live lessons, Bayesian statistics itself has really today become a type of machine learning. So while Bayesian statistics is even older than frequentist statistics, it is being applied today in situations where we have a lot of data, and so it would have been impossible in centuries past to do anything meaningful with those statistics. But today we can use it as a machine learning approach where the sample sizes aren't crazy large, and typically we have evidence for priors. So because Bayesian stats can be computationally expensive, we might not always apply it in situations where we have very large data sets. I'm sure there's probably exceptions to that and ways of working around it. But the big thing is that Bayesian stats is useful if we have evidence for our priors, for our initial parameter values. So instead of having all of our model parameters be random initially, we could, with the power of Bayesian statistics, use prior evidence, prior experimental evidence or logic, or in some cases maybe even educated guesses as to what good starting values for some of our model parameters might be, and then we adjust those priors based on training data. All right, so that's enough of an introduction to statistics and why it's useful for machine learning applications. Up next, we're going to start learning some new statistical theory.